First of all, I should say a big thank you to all of my students who have been with me in the field over the last 15 or 20 years or so. And they are a constant source of inspiration and knowledge and challenges, of course. So thanks to all of them. Here is the principal take-home message. All right. We know very little about the early Earth, and therefore it's such an interesting thing to talk about. We do know a bit, right? We know just enough to talk endlessly about it, but we do not know enough to supply you with firm numbers that would put any issue firmly to a rest. So many of the topics we don't know much about include the following here: continents, weathering, coasts, tides, oceans, the atmosphere, the climate and the weather, volcanism, meteorites, radiation, and the list goes on and on and on. And maybe at the end of the talk I will ask you what important topics I didn't even mention. And I'm sure you will have a couple of them in mind. One of the topics I will not talk about at all is probably the most important of them all, at the very bottom, and also firmly rooted in the second half of the common topic here of astrobiology. I will not talk about biology. I will just talk about the cradle. I will not talk about the baby. Okay? I'll leave that to more competent speakers later on in this workshop. So let me go back into geological time and describe what we see, or rather what we thought that there might have been. And so here you see the geological time scale, and I'm going always from left to right, and I try to be consistent in the names and in the colors here. We start at 4.56 and we go all the way to the present here on the right, right? And you may think that this may have been a rather uneventful time period. The Archean here, the second of the four major eons we count in Earth history, but far from so, right? It was a time that really laid the foundations to the Earth system. And my students always complain about me spending almost half of the Earth history class in the Archean. And then by the time we have the last three lecture hours, I finally get into the Phanerozoic. And then I do Cambrian, Ordovician, Devonian in 1 hour. No, Cambrian, Ordovician, Silurian, Devonian, Carboniferous, Perm in the second hour. Third hour gets the Triassic, Jurassic, Cretaceous. And then in the last 10 minutes or maybe 15 minutes, I do the Tertiary. And I say, Quaternary, that's really a subject for the geographers. Just go over there. And so it's pretty funny, but I think it's important, right? It's such a fundamental time period in the formation of our planet, and you see what has happened there, right? We started out with life fairly early on. We will come later to the problematic relationship between life and geology. So chemosynthesis, first by archaea, then by chemotrophic bacteria. You see that I put that explosion symbol of photosynthesis rather early on, even in the Hadean. Maybe a bit later, we don't quite know about that. It's just a hypothesis for the time being. We had initially aerobic life, and then you all know about the great oxidation event or great oxidation revolution around 2.3 that firmly put oxygen into the atmosphere and also into the oceans. But of course, oxygen was or had been produced by photosynthetic organisms for hundreds of millions of years earlier, right? So from an organismic point of view, the first half of Earth history was the bacteria planet. So at your next intergalactic conference, when someone from Sirius or Aldebaran asks you what the dominant life form on your planet is or has been, considering that glimpse of geological time that we have been around and that we will be around, the correct answer would be that our planet is dominated by bacteria, right? Both from a volume as well as from a historical perspective. So it's the bacteria planet. And you see down here we have the eukaryota coming in, and predation, that big lifestyle change that essentially Remember the mussels you ate for lunch? It's also a product of predation that comes in at the last 10% of Earth history. Let's focus a bit here on that red frame here on the left-hand side. That is the Archean. So now we have blown up the scale here a bit, and we only go from 4.56 to 2.5. By the way, these numbers, 4.0 to 2.5, they were purely formed by committee. The Archean starts the 1st of April 4 billion years ago, and it ends the 1st of April 2.5 billion years ago. And they have no significance in geology or in Earth history. We are about to change that, we hope so, but you know, changing calendars is usually a big thing. It's not easy. So here you see the geological significance of the Archean, and you already see our problem we have from a geological perspective. We just have no material, okay? In the Archean, we don't have any rocks at all. We just have a couple of minerals, really. We have the oldest, well, and a couple of gneisses and so on, right here at 4.0. That is rocks that have been at least viscous, if not fluid, and they have seen temperatures of 500, 600, 700 degrees, and were deep within the crust. The oldest surface rocks are 3.8, 3.9 billion years old. They are in Greenland. The oldest well-preserved strata are start around 3.6 billion years ago. They are largely volcanic, and only around 200 million years later come in the first decent sediments, strata that you can walk along and follow for a few hundreds meters or a few kilometers, and really think about in what environments they may have been laid down. Plate tectonics, as we know it, another big mystery. There are people who say it started on the 1st of April 3 billion years ago, okay? But also the opinions diverge wildly. And nevertheless, we have within the Archean also a rich biological record. And so I will talk about life just a very short bit. As you see, we have, and you see our record of life goes back in geological time. The longer, the looser you put the constraints. If you want to have a real fossil in your hand, right? That is, you would like to see it with your naked eye. You can go back about 3.5 billion years. If you put your constraint a bit looser and you say, I'm satisfied with a photograph that I have taken through a microscope, you can go back another 100 million years to about 3.6. If you think you're satisfied just with a shape in a rock that may or may not resemble an organism that you may or may not have seen in a textbook or in a zoo or somewhere or in some collection, you may go back another 50 million years to about 3.65. Shape fossils, not really body fossils anymore. Then you go back to chemistry. So I know there are many chemists among you, and the oldest chemofossils are about 3.8 billion years. And if you put your constraints even looser and you're satisfied even with just an isotopic ratio, then of course you can make a big leap and you go back another 400 million years. So if you really want to be generous, you could say the oldest fossils are about 4.4 billion years old, but I will show you in a minute what they consist of. Okay? One big part of the problem is that we have no material, that Earth has been a highly dynamic planet, and that is not just a platitude. The recycling on our planet just has been relentless, and therefore typically most rocks get recycled in the present-day plate tectonic cycle of opening and closing of oceans approximately every 180 million years. So if we go back to the first third or the first quarter of Earth history, you have that up and down, open and close life of the continents going on 10 times. And there are virtually no rocks that have been left unmetamorphosed and undeformed or not been recycled. And therefore, we count among the Precambrian rocks all those that is older than 540 million years, all those that are shown here in blue. And if you go back into the Archean, that is older than 2.5, then you see the rocks here in red. However, many of them, having been the oldest, are also in the very center of the continents. Being in the center of a continent means that it's typically flat. And if you're in low latitudes, it also means that you have thick soils and no outcrops. So many of these red spots or red regions here are pretty much unusable. We have, if you wanted to really examine the oldest well-preserved strata, then you only have 2 regions available in the world aside from that tiny speck up here, Ishua in Greenland. Namely, you have the Karpwald Craton down here in southern Africa, and you have the Pilbara Craton. No laser? Okay. You have the Pilbara Craton here in northwest Australia. Pilbara looks like this. And I know Camille has been there, right? You have, presumably, or did just your rocks come from there? No, you've been there, and some of you probably have too. Pilbara looks like this, okay? It's subtropical. It has been stripped of its cover rocks already in the Cretaceous. The landscape has been planed off. There are cyclones and hurricanes going over there every summer. It's low relief, and all these neat little green things that you see here, that's this famous spinifex, which I see Camille already has fond memories of. So that's Pilbara. It's rather large, but it's low relief. And the other area that I much prefer, and many scientists actually do that, many other scientists, I should say, do that as well, is the Barberton mountain land in South Africa and Swaziland. Here in the middle background, you see the highest point made of the mists. It's 1,903 meters high. The lowest point in the Barberton Greenstone Belt is about 200 meters high and lies in the Kruger National Park. So you have a topographic relief of about 1,700 meters. And these rocks have been stripped of their cover rocks and seen the light, so to speak, and unfortunately also the atmosphere, only about a few 100,000 to 1 million years ago. Okay? So these are the 2 data points we have worldwide. Incidentally, the Barberton mountain land is about 160, 140 kilometers long and about 30 kilometers wide. And for those who'd rather have a comparison, that's pretty exactly the size of the Lance de Gascogne. Okay? It's about 100 by 30 kilometers in size. So think about if all you had left of present-day Earth was the Lance de Gascogne. Would you dare to make any inferences about the state of planet Earth in the last 500 million years? Just a summary statement. You probably wouldn't. Yeah. You would not be well advised to do that anyway, but people do it. So I think you see that anything I say for the remainder of the talk should be taken by you with a grain or a very large grain, maybe a mountain of salt, all right? Don't believe anything. For example, you may or may not believe this here, and I only will show 3 slides for the first 500 million years of Earth history, right? Because this was supposed to be Hervé Martin's talk. But you all know that, and it's just meant to remind you how Earth came about from that initially solid cold accretion and then the heating up through the core formation, the so-called iron catastrophe, the release of vast amounts of potential energy as all the iron went down into the core, and also the high radioactivity, occasional impacts. So you have that Hadean magma ocean, and which may not have lasted very long. You formed the first solid surfaces. You had that primordial rain. That's why I chose this version of these many magma ocean artist impressions, because they have these nice thunderstorms here. And the primordial rain, some of you may be experts in that topic, may have lasted a couple of 10,000, couple 100,000 years. That's where the atmosphere, which had gassed out from the molten interior, finally precipitated and formed the first oceans. Of course, the surface, even though it formed solid, was still hot. And so the early interaction between the magma the lithosphere, of the geosphere rather, and the overlying liquid fluid body was rather violent and gave rise to extreme close interaction of solubility and precipitation of all the materials that were dissolved or fragmented within the waters. And you may be familiar with that hypothesis that this magma ocean episode that gave the Hadean. Hadean is the Greek word for hell, right? So the hellish period, the hellish eon, all 500 million years of it. You may be aware that there's a theory came out almost 15 years ago now, talking about the cool early Earth, right? And that was based on isotopes, and it was based on first granites, and some of the characteristics in these granites showed that these granites interacted with liquid water a few kilometers higher, right? And that theory then got an additional twist, right? Because people became attentive, and when they heard the word water at 4.4, and where there's water, there should be life, possibly. So people started looking for life. And here you have that oldest fossils, which I promised to you, which judge for yourself, right? And so people started looking within a granite for fossils. So you can't really do that unless you have some components from the surface, from the aqueous surface, included within some grains, within a crystallizing magma. And sure enough, people found that. People first got themselves some really old material, and you see here an image of one of these extremely old zircon grains, which Camille have already mentioned, right? Zircons are really resistant, but rather common trace minerals in granitic and granodioritic melts. And you can date them because they include uranium, which decays to lead. So you have these tiny sand grains, which easily will fit underneath your fingernail. And of those, we have a couple of 10,000 from a single location on Earth. The Jack Hills conglomerate in Western Australia, out in the outback. So the Bell et al. Here in a really interesting study selected, or they went through 10,000s of these zircon grains, and they indeed found at the very end a couple of those that had some inclusions here that you see here. Okay, many of the inclusions in the grains they found were just opaque ore minerals, ilmenite, pyrite, magnetite, and so on. They had to be taken out. But out of these, I think, several hundred grains, 2 were left that actually were the black, the dark inclusions consisted of carbon. Okay, and now one of the grains had a big crack going through it, and so they only had, of the 2 grains, 1 left. And they put the laser on these dark grains here, and it surely had a negative delta 13C carbon isotope anomaly, indicative of having interacted with water and with life. Okay, so the idea is that somewhere above this granite in which the zircon here crystallized, there may have been a body of water, and there may have been some shale, and so you form black shale with organic matter in it, and somehow you have some sort of subduction or subduction, and you get that shale down into the magma chamber, and of course it breaks up and it starts boiling, and it becomes redigested into the magma. But somehow a couple of little specks survive, and they become entombed, crystallized within a zircon grain, oldest fossil. So life may have, the upshot of that study is, and the authors were very careful to tone down the message. The upshot of that message of that paper was that life may have originated rather early on planet Earth, at around 4.4. However, for the next 400 or 500 million years, which is not a short time span, even by geological perspectives, we have no surface record. Okay? I'll go through this talk in highlighting I think, a total of 6 or maybe 7 surface-forming agents. Number 1 is meteorites. Okay? And you have heard from Alessandro already 2 days ago that Earth has seen quite a bit of its share of meteorite impacts, probably at the same rate and the same number as the Moon has. You know, nearby, same orbit essentially, so why not? And while everything has been very nicely preserved on Moon, that's why we should go there again someday to learn more about the Hadean and the Archean. Everything has been resurfaced and recycled on Earth, right? So by now we know quite a bit of Moon, on the Moon, and we know a crater stratigraphy because the Apollo astronauts brought back a total of about almost 400 kilograms of samples, all of which have been dated. So they had these samples, of course, were taken at strategic points where the impact masses from these craters overlapped each other. So by dating them, you could build a layer cake stratigraphy of old craters and younger craters. And that led to this beautiful colored map here that you see on the right-hand side, a crater stratigraphy geological age map of the Moon based on 2,400 samples. Okay? And therefore, we can reconstruct the impact history of meteorite craters on Moon. I'm sure this is nothing new to you, and you may have seen similar diagrams here before, so I'll go through this rather quickly. We are interested in this time period, and what you're seeing here plotted is, of course, our geological timescale from early Earth to the present, and this here is the cumulative craters greater than 4 kilometers. And what is plotted there are actually the numbers per square kilometers, right? And this is logarithmic, as you see. So, and subdivided by age, based on all that dating that the Apollo astronaut and NASA scientists and others have done. And the important thing to see is that during the Archean, the meteorite impact and cratering rate decreased down to about 10% of its value at the beginning of the Archean, right? At the beginning of the Archean, we may have been anywhere between this point and that point, somewhere in the middle here, around 5 to the 10 minus 3. And at the end of the Archean, we were over here, okay? And so now remember, we do have a couple of outcrops, right? And in Barberton and in Pilbara from the Archean, from the middle Archean, so it would be reasonable to expect that we should see evidence of the same impact flux that hit the Moon at that time also on Earth. And indeed we do. As we go out into the field and we carefully look at the rock outcrops, some of you who are not geologists may think that we just wander these hills aimlessly and then enjoy the view and then go home and drink a beer, but we do it just the way you go into your laboratory. That is, we think about a problem, we devise a hypothesis, we then think about our methods, we get funded, or rather, usually we do not get funded, and then we just take an honorary round, and finally we get funded, and then we go out into the field and check our hypothesis, right, against the rock record. And then comes the difficult part, you have to write it up. So when you go out into the field and you look carefully, but you have to look with something in your mind. You need to go look for meteorite impact beds, okay? Then you find beds like these here. These are sandstone beds, okay? And the sandstone consists of rather well-rounded and unusually coarse-grained, and at the same time, you may notice that unusually well-sorted sand grains. Yeah, there's no larger and smaller in here. They're all the same grains. They're all the same grain size. This is a so-called impact spheral bed. That is a layer of sand or sandstone that was made from sand that originated from melt droplets that had been originated by giant impacts on the other side of the world, had been orbitally transported around to the other side of the world and then rained out over a time period from hours to months. Okay? When you drill through there, you see that's what they look like in a core. The scale here is in centimeters. When you go at it with a microscope, that's just a conventional digital microscope here, you see that these spherules are actually built a bit like an egg. They have a hard outer shell and crystals growing inward. Yeah, that is, they crystallized from the outside. These were melt droplets, okay, that rained out from the atmosphere in a molten state. And by now, in the Barberton Greenstone Belt, that spans a time period of about 250 million years, we have 10 of them. No, 8. I'll show you the figure. In the significance of these spheral beds is that indeed they were generated here on the left-hand side of the image, somewhere on the other side of the world, by meteorite impacts with a bolide measuring anywhere between 10 and maybe 50 kilometers in diameter. Then there are the crater scaling laws, right? You multiply by 15 or so. So you generate a crater of a dimension of maybe 500 kilometers diameter, and you inject a certain volume of vaporized and molten and fragmented rock material, a mixture both of the target and the impactor, into orbit, and from there you rain it out equally in more or less equal thickness around the world. This has two consequences. First, as these molten droplets rain down through the atmosphere, they cool and transfer their heat to the atmosphere. The atmosphere becomes a couple of 100 degrees Celsius hot. And the atmosphere, within hours, probably hours to days, the atmosphere in turn transfers its heat to the oceans. And the oceans will start boiling from the top. Okay? And that, of course, then has all kinds of consequences for chemistry and obviously for biology. So I'll come back to that. And so here's the stratigraphy of the Barberton Greenstone Belt, that kind of tiny piece of Archean crust we have left. And the details don't matter. But this here is the base, and the scale here to the left is in kilometers. So you see these are, I think, 11 kilometers, which is underneath that red label here. And then you have another few hundred meters on top of here. And this here, these 2 kilometers belong to the top over here. So overall, you're looking at about a 12-kilometer thick rock sequence. And it spans down here in the age from 3481 all the way up here to 3243, so about 240 million years. Now, don't think that we have to drill down through 10 kilometers of rock to get this. All these rocks have been crumbled and folded. They stand on end, okay, like the pages of a book. The strata go down more or less vertically into the ground, and as we map them, we walk over them and look at them essentially sideways, like in a profile. Yeah, and here in the quarries right next to, just before we reach Bordeaux here, there are beautiful limestone quarries, and all the strata lie horizontal. But in Barberton, everything is vertical, and we usually walk with our noses down to the ground, right? So there's no need for drilling in order to get that 10-kilometer thick rock record, that stratigraphic time recorder. Now look at these red squares again, and you see there are 3, 5, 7, there are 8 of them, okay? 8 of these big meteorite impact beds. Each of these spheral layers is between 10 centimeters and 1.5 meters thick. In comparison, the KT impact that, in popular notion, extinguished the dinosaurs, generated a local spheral bed about 1 to 2 centimeters thick. Okay, so these were giant impacts that certainly had its relevance on Earth. There was a really interesting paper that came out, I think 2 years ago, by Don Lowe and Gary Byerly, and with the title you read here, "The Geological Record of Partial Ocean Evaporation Triggered by Giant Asteroid Impacts." This came out in Geology. Geology is a monthly magazine, monthly journal that limits its contributions to 4 pages only. So you have to be really succinct, and Geology prides itself on getting out timely and provocative items. So Don and Gary, both being old and experienced geologists, have mastered the art of writing manuscripts that are irresistible to the editors. And here you see parts of the last 2 sentences. Conditions, they're talking about a particular outcrop, conditions that would have characterized shallow marine environments in a boiling Archean ocean. That's what they observe in a about 5 meter high outcrop in the Barberton Greenstone Belt. We suggest that the silica crust was deposited, that's what they found there, silica crust was deposited as a rim of siliceous sinter fringing the ocean, when ocean surface layers were essentially a global hot spring. Yeah, so nice comparison. You're boiling the oceans for a couple hundred years. There has been another study by Stephen Moishes and Oleg Abramov at UC Boulder a few years ago, and they invented essentially a numerical sandbox. And you see that sandbox here. It has a y dimension here of 25,000 kilometers, and here an x dimension of 25,000 kilometers. You're essentially looking at the surface of the Earth, more or less. And the thickness here is far less. It's only about 150 kilometers. So thickness of the rigid outer layer of the Earth, it's essentially the lithosphere. And then they numerically peppered the surface with impacts. And they just chose the right mix of different sizes and the right impact rate that we would assume for the Hadean and the early Archean, and trying to figure out whether the crust would ever become hot enough to eradicate all life. And what you see here in color, you have the temperature scale. That is not the case. Yeah? Even though the meteorite flux may have been high in the Archean, in particular in the early Archean, and you remember the late heavy bombardment, whether it may be for real or not, we certainly had a high impact flux. But anyway, geological time is so immense that the Earth's crust had time to cool down to these low blue temperatures between these major meteorite impacts. What I found more interesting, however, and which is not being directly addressed by Steve Moishes and Oleg Abramov, is whether these impacts heated up the hydrosphere sufficiently to vaporize it entirely or only partially, right? It's not so much a matter of heating up the lithosphere here in different colors of orange, but rather in evaporating the oceans. Hervé Martin was supposed to have talked about this topic here, but so I'll just spend a couple of slides here. Tectonics and continental growth. Why is that important? Without continents, no life. Okay, I see a couple of surprised faces. Do you know how the argumentation goes? We have, and that's important for exoplanet exploration, right? Maybe we should direct our exoplanet search for continents, for planets that have continents. We might be able to see continents, right? But I'll tell you why it works. So we need continents. And of course, the current process of building continents is plate tectonics. So it would be really important to answer the question whether and when we had plate tectonics operating as a continent factory. And there has been this big controversy in the last 20, 25, 30 years between the non-plate tectonicists and the plate tectonicists. And out of that beautiful little textbook, it's not a little textbook, out of that beautiful textbook that I was given 2 days ago by Muriel, I shamelessly photographed this figure here by Bédard, 2006, that shows what I call the lava lamp tectonics, or other people call partial convective overturn, the alternative to plate tectonics, or probably even a necessary alternative to plate tectonics, because in the Hadean and the Archean Earth was so hot that plate tectonics was insufficient to cool it down. If we only had plate tectonics back then, Earth would have heated up. Okay? Think about yourself as Earth. Okay, and you're hot. What do? Well, you try to get air to your face. You try to invigorate convection. You try to not to dress too warmly, all your veins open up and your heart starts pumping, getting the hot or excessively warm blood to the outer surface and so on. Earth works essentially, unconsciously obviously, in the same way. Okay? Plate tectonics wouldn't have worked. Earth needed a faster and more efficient method to get heat up to the surface, okay, where it could cool down. These huge convection cells, with these ascending branches and then long horizontal branches and descending branches that we see as plates up there on the surface of the Earth would have been insufficient to cool Earth down. So people talk about this kind of vertically dominated tectonics mostly in order to transport heat. Okay, and Bedar here, who probably invented the modern concept, has a two-level diaperic or subduction concept. You see that up here these green heavy volcanics sag down into a lower crust that is lighter. And then here at the base of the mantle, he does the same thing. There he has a so-called depleted mantle. This is the material that is left over after the orange stuff has been segregated from it and has risen. And that becomes too heavy after a while too. It's called a rest height. And that sinks down into the mantle. So it's like an inverse diaperism. Okay? And that is a very efficient process of getting heat away from the core and making heat escape into outer space. The concept then was popularized a few years later by Martin van Kranendonk, a professor at Sydney. And Martin is really good at drawing these back of the envelope sketches. So his title to that is partial convective overturn. Partial, only a part. Convective, it works through convection, and it's an overturn. All right. So he starts like this. These are diagrammatic cross-sections, and he forms basins, greenstone belts. They are getting filled with sediments and volcanics. And to the left and to the right, you see these lightweight plutons rising. So initially, you have a bit of extension. See that? How space is created. And as the drop develops and you get into space problems, so that is followed by shortening and reverse faulting. You see here you're getting into space problems, and the layers in particular in the center are getting crumpled up, while out here you still have lots of space. And in the third phase, things have just narrowed down and are starting to drop off. Okay, this is where the shortening is at its highest. This is how Martin explains the origin of greenstone belts. So if you put these figures, in particular the third stage here, next to each other, an interesting pattern in cross-sections developed, right? This here is the initial stage. Then you have a mature stage and an over-mature stage. And you see here in the middle these big plutons rising to the surface. And in between you see the volcano sedimentary fill of these original basins or these volcanic plateaus that consisted of these heavy iron and magnesium-rich volcanics just fold and sink down. Imagine Hawaii. Not just the big island, you just take the whole archipelago, and it was deposited like this, right? And my palms and fingers is now a shield volcano, and here you have another shield volcano, and you just fold the whole thing, and as you do that, you also turn it sideways, and down it goes. So that's what we see in these greenstone belts. We're looking at a cross-section of volcanic plateaus sideways, looking down at them. Okay? You take it, you fold it, and down it goes. So here this is the concept in cross-section, and if you look at that in a map view, here is the geological map of Pilbara, northwest Australia, the other terrain, right, that we have left over from early Archean crustal formation. And you see that pattern. In red, you have the plutons, and in green, as Camille has shown you earlier, just before lunch, you have these greenstone belts filled by sediments and by volcanics. The red are plutonic rocks that have risen, the green are the belts that have gone down. This is a pattern that we see nowhere else after 2.5 billion years. Modern origins. Think of the Cordillera between Alaska and Patagonia. Think of the Alpine chain between Portugal and New Guinea. They are linear belts. They do not show this egg-shaped up and down pattern. Okay, so this is really strong evidence. And I will also show you now in the following slide the pattern from Barberton. Just remember that Pilbara is a lot larger than Barberton. The Barberton belt would represent in length just about one of these green stripes here. Okay, so but that's what you have here. And also you see Barberton has that ovoid pattern and a cuspate lobate shape of these volcanic sequences in between, representing vertical tectonics. And then when you go into the mountains that are shown here by these yellow and brown rock strata and map their deformation style, you indeed come up with these particular fold shapes that are rather rare in modern day mountain ranges. Yeah, suggesting that back then we are looking at a fundamentally different style of making continents, stabilizing continents vertically rather than horizontally, yeah, as present day continents are characterized. So people called this here mushroom folds and canoe synclines like this here, yeah, because some of these shapes resemble the bows or the sterns of these Canadian canoes. And if we do this, so these were old hand-drawn figures, but over the last 2 years or so, we have started doing this in a more quantitative fashion by digitizing everything and extending these fold structures both into the subsurface, as you see here, as well as into the air. And we find that these greenstone belts are indeed highly compressed and highly vertically strung out origins, vertically strung out. That is something we never see in modern tectonics. So the overall belt, to come back now to surface conditions, imagine what such a greenstone belt should have looked, what today is a greenstone belt, what an environment that is represented by a greenstone belt should have looked like back then. Well, you had these mushroom or round islands coming up, and maybe they coalesced in between. And in between you had sedimentary basins that were kind of funnel-like, yeah, and meandering and furrow-like. They constantly deepened, and of course sediment was shed from these rising plutons left and right, and maybe, I'll come to that, the tides washed the sediments back and forth. So it may have looked a bit like a fjord environment. We don't know. We know, however, that whatever happened went on rather quickly. We are looking at uplift rates of about millimeters per year. Yeah, 1 millimeter per year is a lot. Yeah, because you get 1,000 millimeters, 1 meter in 1,000 years. Since the Middle Ages or since the Romans, you'd have 2 meters of sediment, recording in a millimeter every single year. Okay, so as this year goes up, this year goes down at the same rate, at millimeters per year. And after all, in yellow, this is our time recorder. What goes up here gets eroded and is not there anymore. What is in yellow goes down and is preserved. So we have in some of these Archean greenstone belts, due to their high subsidence rates at millimeters per year, meters per 1,000 years, kilometers per million year, and in their 3 to 5 kilometer thick sequences, we have extremely high magnification time recorders of Archean events. Millimeters per year, by the way, is also approximately the rate at which sediments are getting deposited these days here in the Gironde estuary, in the Thames estuary, in front of the Mississippi, along passive margins worldwide. Millimeters per year would allow you to see almost every major storm. So to finish off this topic of tectonics, I typically ask my students in Earth history class to put themselves into the role of a space explorer. Let it be, let's say, a scout of the Klingon fleet. All right, some of you watch Star Trek, good. And you only have 5 days to explore that strange solar system with its 9 planets, and the only tool you have on your little scout cruiser is a radar altimeter. So you're quickly doing a survey and you're getting back the altimetry data from these 3 planets, and your report is due or overdue to your admiral to recommend a planet for invasion or destruction or colonization or friendly commerce. Yeah, we heard this morning talks. Which planet do you choose? The altimeter is all you have. Don't start with water and so on, okay? The blue is just low and the orange is high. And don't tell me about vegetation. Green is not vegetation. Which planet do you choose? Quickly, your report. The third. That's easy. The question is why? You don't know about continents, you are Klingon. What is happening on that third planet? Something is happening that, let me put this more general, something is happening that subdivides the topography into highs and lows. There's a process going on that separates very efficiently. And if highs and lows are dominated by gravity, right? Heavy rocks, lightweight rocks float, yeah, they form continents, then there must be a process going on that is forming this scum, these lightweight continents floating on the denser stuff. There must be Mars too, no? In part, but not much linear ridges on Mars. Yeah, not much linearity. Look at this beautiful linearity, and on that third planet you have the highest elevations right next to some of the lowest elevations, and you hardly have any of these odd concentric patterns that, even though you are Klingon, you kind of know what that means. So whereas why is that planet either not hit by these objects that make these circular depressions, or it has somehow developed a method to obviate them? Something is going on. There's a long-term dynamic process going on that third planet. Okay, it creates these big depressions, and it creates right next to these big linear trenches these high mountains, and there's erosion going on and sedimentation. So even though you as a Klingon junior scout in your little spaceship may not understand exactly what's going on, you are right with your recommendation that the third planet is the most interesting. So now I'm coming back to these continents, right? Continents are a prerequisite for life. Why should that be? Well, for a couple of reasons. First, if you have continents, yeah, you have a chance to make shallow water environments. And even more, you make subaerially exposed environments. They can be eroded. They can weather. Okay? They can be subjected to a mix of H2O and CO2. Okay? You have silicate weathering. You can wash the products of that weathering into the margins of the continents, supplying nutrients. If you have a shallow water environment, you have that wonderful, unique mix of liquid H2O, of sunlight, liquid H2O from the right, sunlight from above, and nutrients from the left. Okay? And now if you invented life, then you are free home. Okay? So that is the beauty of continents. Continents are necessary for almost everything. And there are learned papers about continents, and Tilman Spoon is one of the main authors along this line of thought. This has not grown on my own mind. The map up there is one of my favorite topographic maps, because in black the continents, but more importantly in red are the flooded continental margins, the so-called shelves. Okay? We have a lot of them, and we need them for photic factories. Yeah? Pull out the CO2 out of the water and make shells. Yeah? And that gets us to the atmosphere. And I think the atmosphere is my last point prior to the break. Faint young sun paradox, you're all familiar with that, right? I can quickly click through that. You have here back at 4.0, the solar luminosity was probably around 75%. Now it's here to the right at 0, it's up to 100%, no big deal. Corresponding with a temperature increase anywhere between 240 to 300 kelvins. And so with the lowest luminosity, you only get a low effective temperature. However, if you give the Earth its sweater made of atmospheric gases, you have a greenhouse effect, so you're able to lift that surface temperature a bit higher. And still, it's not enough to get above the freezing point of water, okay, at 273. So yeah, so you would expect Earth to have been frozen for the first half of its history, and only thereafter temperature has climbed effectively. How do we get around that? Because in the face of evidence that the early Earth was not cold at all, rather it was probably hot, well, you just need to raise that upper limit of that gray greenhouse gas envelope anywhere up here. However, you need to have a different mix of greenhouse gases. These 0.003% of CO2 and the water vapor will not do it. So we need to think about putting on additional layers, right? It's just like putting on a sweater or another t-shirt and so on, and you need to think about different greenhouse gases. And this here is the composition of the usual suspects, the big gas contributions that you have to the atmosphere. Most of them resulting from the outgassing. Some of them may be biogenic. And what you should remember is it's a very different atmosphere, okay? Oxygen-free, it's reducing, it's dense, it's moist, it's dusty due to the volcanism. It probably was hot, and I put toxic, of course, in parentheses because it's toxic to us metazoans, okay? Many other organisms, it's just the atmosphere they need. And so what gases do we have available to make a nice greenhouse effect? They are, again, the usual three suspects: NH3, the ammoniac, then the methane, and of course CO2. And they all come with their usual advantages and disadvantages. The NH3 in particular is a strong greenhouse gas, but we know that the Earth's atmosphere wasn't strongly reducing, and also it's not lasting very long in the atmosphere. It gets quickly broken up by UV radiation. It's really feeble and a sensitive molecule, and it's also really soluble in water, so it gets washed out. So NH3 may have played a bit of a part, but certainly not a major part, according to current thinking. People have more focused on methane, right, which is also a strong greenhouse gas, but if you mix that with CO2, you get a haze above certain concentrations. And a haze up in the stratosphere is certainly not what you want, right, because it would shield your surface from radiation, it would absorb the radiation and reflect it back, and also CH4 is it will be washed out after a while. And so left, of course, is then CO2, which is only a weak greenhouse gas, but it's ubiquitous and it's rather stable. And however, we cannot really afford to put a lot of CO2 into our atmosphere, at least not that much as required to lift the temperatures to acceptable levels, because then our rain would become too acidic. And we know from the rock record, from just looking at the minerals from which the shales and the sandstones and so on and the limestones are made out of, that the Archean rain was not overly acidic. It was slightly acidic. So the paleoclimatologists get together and they draw all these diagrams here that, don't be afraid, this looks a bit complicated, but it really just plots the methane concentration, and you see this is log, and these are log of the partial pressure here in bar. It goes from strongly negative to less negative, so methane increases logarithmically this way, and the same here with CO2, and these diagonals here are then obviously isotherms, right? It becomes in this diagonal from the lower left to the upper right, it becomes warmer as you increase either or both the concentration of methane and CO2. You cannot do that without limits, right? You see in the upper part of that diagram that you develop haze. Yeah, so you want to stay out of that. And you see it on the right with these red hatches here, that you have a paleosoil limit, then which means the rain becomes too acidic and you would dissolve the clay minerals and you would dissolve any carbonaceous calcareous crusts and so on. So you can't have too much of that. However, so what do? Well, you try to push your atmospheric composition into that upper rightmost triangle that is allowed by your boundary constraints. And these are more or less than the concentrations of methane and of CO2 you have. Okay? For a long time, not being a geochemist, I wondered for a long time whether that was allowed at all, having the fully reduced carbon species and the fully oxidized carbon species together. But people tell me that yes, up to certain low concentrations that is possible. Good, some people not, all right? So I'm not entirely wrong. And I'll show you just a second diagram, but I won't bore you with all these here in mid-afternoon with all these XY diagrams. This here again plots CO2 down on the x-axis, but here it plots temperature, and the methane is represented by these isolines. And the methane now increases in these isolines to the upper left. You see the lowest line here is 10 to the minus 5, and the next line towards the upper left is 10 to the minus 4, 10 to the minus 3, 10 to the minus 2. And so overall, people place themselves, you need to put yourself somewhere. Not here at the bottom, because that's too cold. You need to go higher up. But you can't go up, you can't go very high up either, because then you would go into unreasonably high methane concentrations. Okay? So, looking down at our present atmosphere, I would just like to briefly halt here maybe and allow you to develop a bit of appreciation for this image. I did not take that image. I'm too old for that. But you are young enough, all right? Not for taking a flight. It's a really high flight there. You have to go up to the ISS and take these pictures. But look down at that beautiful interplay of water vapor and atmospheric composition and radiation, right? This is unique. We know of no other planet in the universe that would offer such a picture. Okay? Quite likely that there are some, but at least we do not know of any. Okay? And what also impresses me in this particular atmosphere is that it's so incredibly subtly balanced. Yeah? That not because if anything stopped, and occasionally I ask my students to play God and just stop all processes. You know, Earth comes to a grinding halt, Earth rotation, photosynthesis stops, weathering stops, whatnot. How quickly would we run out of oxygen? You know, because oxygen constantly gets consumed. It gets drawn down into the rocks by weathering of minerals, after all, oxidation weathering. Yeah, just put your car outside. It's made of metal, okay? So the iron will draw oxygen out of with the help of some water, liquid water, will draw oxygen out of the atmosphere and convert it to rust. So the gas oxygen has been converted to the solid goethite or hematite, all right? So if we did that for a while, if we just stopped, you see that if we stopped the production of oxygen, all of the oxygen would disappear from the atmosphere within a couple of thousand years. It has to be constantly resupplied. We really need the biosphere, but to no big surprise. But also consider that nearly all the CO2, that's the second point here, all the CO2 is trapped in carbonates and in organic matter. That is, we don't have it in the atmosphere, as Venus does. Okay, over the geologic time, the biosphere has tirelessly worked to pull the gas, CO2, out of the atmosphere and to either put it into organic matter and put it into some black shales or gas hydrates or petroleum or whatnot, or they put it into, these are all liquids mostly, liquids or gases deep in the earth crust, or put it into shells, right, into skeletons and so on. And that is all the conversion, the pull out of gas by the biosphere and storing it on the world's shelves for the largest part as limestones. Okay? If that was not the case, we'd have a pressure of 27 bar. Most water is in the liquid form. Just go outside and you see that. If it wasn't, we'd have 220 bars in the atmosphere. That was these were the Hadean conditions. And lastly, what I'm always impressed by is, of course, we need the CO2 as a greenhouse gas. So not too much, not too little. And if everything stopped and the plants used up the CO2, after all they need the CO2, all the CO2 would disappear at constant rates. Practically this would not happen, but at constant rates, the CO2 would disappear within about 10 to 12 years from the atmosphere. So it needs to be constantly resupplied by CO2 output back into the atmosphere, either by decay of organic matter or by volcanism, short-term, long-term, or by what we do by burning our fossil fuels. So that interaction between the atmosphere up there in that white fog and the bare surface here, represented by the geosphere, became extremely important right from the first minute that you had these first islands of solid lava floating around in the magma oceans. And the most principal reaction there, of course, is that long-term control on CO2 in the atmosphere through silicate weathering. And I'm sure you're familiar with what happens when it rains onto rock, right? The rock weathers. And the way it works is, it doesn't work when you take distilled water and put it on a feldspar. Feldspar is the most common mineral in the Earth's crust, right? 60 or 70% of the Earth's crust are made of feldspars. Here you see the feldspar composition. So it doesn't work with distilled water. You need to add the CO2 from the atmosphere to make this weak acid here, the carbonic acid. And then you have that feldspar, and the feldspar, here you have that carbonic acid, some water here, and you make a clay mineral, and the rest I would simply say you wash away, okay? These are ions. You see, this is a potassium, and here you have the carbonate, and the potassium and the carbonate, of course, recombine. If you replace the potassium with calcium, you'd get calcite, you get limestone, okay? So here, what you then did in effect is move that CO2 molecule from the gas in the atmosphere into the rock, okay? Neat. Back in the Archean, did we have really such high CO2, and can we show it? Yes, we can, okay? And we do that by looking at weathering rinds of pebbles and cobbles, okay? Of conglomerate clasts, in other words. These really need to be Archean weathering rinds. So we need to make sure we go to the rock record, we cut it open. Here you have a conglomerate in cross-section. These, you see the scale in centimeters. Sorry, it's reversed. And so each of these clasts here are a few centimeters in size. The one to the right here is a volcanic rock. And you see it's fresh on the inside, and it has a weathering rind, okay? And you see that this weathering rind is ancient. It just is around that one rock. It does not, that one clast. It does not go around through the entire rock, okay? It acquired this weathering rind in the Archean. And then, of course, you can do the analyses, and it turns out it mostly consists of dolomite and of siderite, both minerals that are high in CO2. And you would get that only if you had high CO2. Today, when you put a volcanic rock out into the rain, think of the Massif Central, and you take some recent volcanic rock and you put it in your rain gutter or anywhere, what will happen to it? It will dissolve to clay, okay? It will not acquire a siderite or a dolomite rind here. No, it will usually form clay minerals because our CO2 content now is low enough. But back then we see all these carbonate rinds, and we see carbonate concretions in the paleosoils, indicating that we did have a rather high atmospheric CO2. Temperature is a big unknown. We have here our time scale, and this here is the paleo temperature, inferred seawater temperature, it says, okay? Currently it's 4 degrees here in the deep oceans and a bit higher at the surface. Here you have in different colors 3 different records from chert silicon isotopes. In light blue, in the dark blue line is delta 18O, from oxygen in chert, and in red you have carbonates. And now each of these curves has its big problems, and one of the big problems we indeed have for the Archean is that we are not sure about how to calibrate things right. But you see all three lines go upward, suggesting that Archean oceans indeed were hotter than today's. Okay, and the Archean seawater composition was vastly different from today's. Right, you see it's anoxic. So in anoxic waters, then iron dissolves rather easily. So you have some of the oceans were probably saturated with iron, was high in calcium and magnesium from the intensive chemical weathering on land. It was high in SiO2 because you get the silica coming in through all the hydrothermal sea floor alteration from these hot hydrothermal black smokers and white smokers, what you have not on the sea floor. And it was high in dissolved CO2, which you got from the atmosphere. It was low in anything that had to do with a lot of, that required, in all these species and molecules that required a lot of oxygen, right? So it was probably low in sulfate, and therefore we hardly see any gypsum, calcium sulfate with two water molecules. We don't see any phosphates, and we don't see any nitrates. Yeah, nitrates are easily dissolvable anyway. And another big unknown is the salinity. We have no idea whether the Archean or even Hadean oceans were high in Na and Cl or were low. Okay, so you also have to consider that the Archean oceans was in very strong and tight equilibrium with its underlying hot, usually basaltic geosphere, that with abundant mid-oceanic spreading ridges and black smokers, and the interaction was really, really close, right? And only later became the composition of the oceans modified by the atmosphere and by the weathering, right? So we really don't know about the salinity. And on the left, you see alternative one. Did most ions that we have today in making up our ocean salinity outgas into the primordial atmosphere, so that the early oceans were highly, highly saline? Yeah, and from then, just because we have continental margins and we can make basins that are full with evaporites when we only have evaporative conditions. Think of the Mediterranean, think of the Persian Gulf, think of the inland lakes in Australia, for example, so that over Earth history the salinity decreased, or is rather the opposite, the truth that is what you see here on the right-hand side, that ions that make up our today's salinity were gradually washed into the oceans from the weathering of the continents. We can't really tell because we hardly have any evaporites, right? First, we didn't have any big continents with wide and flat continental margins that would give opportunity for evaporative basins. And secondly, even if we had those basins, the salts would be easily dissolved by some orogeny or by some mountain building event in the subsequent geological history. What we do see, however, is even in the very oldest continents, right? And here I have a picture that I only took 2 weeks ago or so in South Africa. Down here you have that basement, and up here you have some of the world's oldest flat-lying sediments. And in those sediments you already see halite concretions. See the little squares here? Yeah, these are halite cubes, the imprints of halite cubes. The halite was dissolved out, but the imprints it left in the soft mud at around 2.7, 2.8 billion years ago were still there. And when we follow these occurrences through the stratigraphic record, we see that we go from normal marine into carbonate deposition, and then typically today we would go into gypsum deposition. Back then we didn't. We went straight into halite deposition. Why? Because the oceans were low in sulfate. Okay? Do you need a break? 5 minutes? Let's check out some phase changes out there in the H2O system. Moon, tides, and spin. The Apollo astronauts left this mirror behind. It's a complicated mirror. It's not just a simple bathroom mirror. And that mirror is being being targeted by a laser, just like this one, but a bit stronger, daily, from an observatory in West Texas. And from the runtime of the laser, so the laser goes all the way through the atmosphere, travels 384,000 kilometers, gets reflected, loses a couple of photons on the way, travels 384,000 kilometers back, and the few photons that make it go through 100 kilometers of terrestrial atmosphere to hit the detector inside that telescope. And I think that measurement, the distance measurement, these few photons that then arrive, is the most efficient or measurement that exists. I once read billions of photons are sent out and 3 make it back, or something like that. So read it up. Anyway, you have the reflector on the moon, and from that you can measure the Earth-Moon distance very precisely, and you do that daily. And the current recession, so you figure out that the moon is not on a circle and it's not on an ellipse either, it's on a spiral around the Earth. And the spiral, the so-called recession rate, that is the increase in distance between moon and Earth, currently is 3.8 centimeters per year, which is a lot. You know, it's like this, 2 fingers or so. So if you trace this back, the moon would have reached the Roche limit where it would break up, due to Earth gravity being stronger than its internal coherence about 2 billion years ago, which can't be because we know that the moon is almost 4.5 billion years old. So the recession rate that is so unusually high today, 3.8 centimeters per year, must have been a lot lower in the past. But we don't know how, okay? And nevertheless, you see just from that simple thought experiment that the Archean moon must have been or was likely much closer to the Earth. Yeah, maybe not quite as in this artist's impression, and even if that artist here was right, then the water surface would probably not have looked like it is shown here. Yeah, it would have sky-high tsunami waves and tidal waves and so on, but it makes a nice image. Okay, so we had probably stronger tides in the Archean. The moon on a closer orbit orbited faster and caused more frequent tides and higher tides. And in particular, you know, when you talk about continental margins and their relevance for all kinds of cycles, you want to know about tides. So we geologists figure out tides in 2 ways. Of course, by looking at rocks. And tidal changes, that is the fluctuation between spring tides, the strong tides, and neap tides, the weak tides, which are currently every 14 days. Remember, when moon, sun, and Earth are lined up, and 14 days later they are lined up the other way. So a lunar month is 28 days, and we have 2 neap and 2 spring tidal cycles each month. Back then, they may have been more frequent. Yeah, so today, if we had daily tidal cycles, we would count between a particularly strong spring tide and the next particularly strong spring tide. How many cycles, if the cycles were daily? 14, right? 28 in a month, but because you have that alignment twice a month, you would have 2 of those cycles. So between springtide and springtide, there may be 14 cycles, 14 daily tidal cycles. So you can figure those out in 2 locations on a coastline. Yeah. First, you need something of a delta, and the delta, so you have a strong fluvial input, like here the Gironde, or take the Elbe or the Thames or whatnot, and whatever sediment is transported here gets shed and transported in subaqueous dunes. So just like an Aeolian dune that you're familiar, but now you are underwater. And these dunes can reach heights of 1 meter or so. So when particularly strong, when you have a spring tide, these faucets, these inclined strata of that tide become a bit thicker, okay? Because on that particular day here, that dune was active for maybe 1 full hour, whereas on all other days it was only active for half an hour, and at these neap tide days it took a break. Okay, it wasn't active at all. So we would count the layers here, and on today's record, if that subaqueous dune faithfully recorded each tidal cycle, we would count between the lowest and the next lowest 14 strata. Okay, that is one way. And we would find that pretty close to the coast, where sand is getting transported by saltation, just like in a dune, right? Salting, jumping along the riverbed or the open inner shelf. And the other place to look for would be out here, right? Way out on the lobe, maybe on the outer shelf that is just faintly affected by the tides. And there the mud would settle. And on days of spring tide, silt would settle, a bit coarser grained, because the currents were capable of getting silt out there. And on the days of neap tides, it would only get the mud out there. So we would have these vertical cycles of silt and shale. Okay, shale and silt, shale and silt, shale and silt. And you can count those. Okay, very few places in the world allowed to do that. And secondly, the time recorder may not stop in that time period. If you had a change in wind direction or current direction and you were missing one of the strata, all of a sudden you would think that the moon was closer and rotating faster, because you're not having 14 cycles anymore, but 13 or 12 or 11. Yeah. But it's just a change in current direction. So it's really iffy. And people have done the numbers. Again, we have very few locations, right? To the right you see modern, and I'm highlighting here in this table. The table says paleotidal and paleo-rotational values for Precambrian cycle rhythms, right? And out of all these lines here, I'm only highlighting two here. That is, how many months do we currently have? 12.4, 12.37. And how many days do we have in a year? A bit more than 364. Now we go back in the geological record, and you see over the last 3,500 million years, we have exactly 3 data points. That's not good, all right? And so under different assumptions, they put in 2 columns here, but you see how the number of 12.5 months gradually increases as we go back into time to a value of about 16 months, lunar months, right? Here we're talking about lunar rates, back to 2,450. No data point for the first half of Earth history. And we can do something similar related to the spin rate of the Earth, and I'll come to spin rate in about 6 or 7 slides. And we currently have 365 days in the year. Spin rate means we see someone sitting on Earth see the sun rising 365 in one orbit around the sun. And we have no reason to assume that Earth's orbit around the sun ever increased or decreased significantly. But the Earth spun faster, right? So as we go back in geological time, we would expect an organism to see, if it had photoreceptor cells like we do, sunrises more often. How much more often? 365, 400, 464, 514. Okay? I'll show that to you graphically to get our conundrum across a bit better. Here you have our usual age. Yeah? The present is here. And we currently have the moon sitting at about 60 Earth radii. In the geological past, it was closer, right? Going down along any of these lines. We only have those 3 data points indicated by a triangle, by a square, an open square, and a filled square. That's all we have. It would be really great to go back to the Moody's group, 3,250 million years old, and figure out a data point that would sit somewhere along this line. It would help us greatly in calculating the lunar recession rate. Okay? There was a paper by a geologist who looked at the one, and I'm convinced, and I would agree, he looked at the one suitable outcrop in the Barwood and Greenstone belt sitting over here next to that creek that shows one of these subaqueous dunes with thick and thin little faucets. Okay? So I have one of my students here taking pictures. The picture he takes is this here, for example. See these inclined strata? Yeah. So sediment transport was from the right to the left. Imagine that you were an ant and you were sliding down the lee phase, the down current phase, yeah, of that current. Do you see any thickening and thinning? Looks pretty good, huh? So anyway, there's this paper out that claims back then the moon went around the Earth not once, well, the lunar months didn't have 28 days, but only between 19 and 21, yeah, because his periodicity was not 14 that he counted, but only between 10 and 11. So this is great fodder, of course, for any competing or colleague scientist. I take my students and go out there, and within an afternoon, 3 teams of 2. One is measuring just with a ruler the thickness of these layers, and the other one is taking down the numbers. Makes great fun. And so we have 3 independent data sets, and then we plot them up and we do a Fourier analysis. We did not see any rhythmicity at all. None of my teams here. So sorry, right? I have never published this because I would like to replace the old data that claim a lunar month of 19 days rather than 28 by something better, but I can't. Yeah, all I have to say is, sorry, I don't believe it, but I can't offer anything better, which is for a scientist, an unsatisfactory position, so I haven't really done very much on that. Anyway, we still have only 3 data points for the Archean for the Precambrian, for the entire Precambrian, from 500 all the way to 4,500 to constrain Earth-Moon interactions. However, we have a couple other factors to consider. 4 additional factors affecting Archean tides. Think about the depth of today's oceans. Yeah? Today's oceans are about 7 to 8 kilometers thick because they consist of basaltic crust that is formed at the mid-oceanic ridges, and they lie adjacent to continental crust that consists of granite. Granite is lighter, so think about of an equilibrium. Here you have a sailboat, yeah, with a low draft, and here you have an aircraft carrier with a deep draft. Okay? Back in the Archean, it was a bit different because the mantle was hotter. It didn't just secrete and extrude a few percent of basalts that went up to form oceanic crust. No, a lot more. Okay? So the draft here was a lot higher, and that is, as the crust sank deeper in, it also was higher up, displacing the oceans up and out. See that? The ocean, the average depth of the ocean is here. The average depth of the ocean is here. The water is getting displaced up, and therefore it's pushed onto the continents. Look where I have the coastline over here. Only a very small part of the continental shelf is flooded. Look where I have it here. So because the oceans were shallower back then, a larger part of the continental margins, maybe all of them, maybe the entire continents, were typically flooded. Secondly, back in the Archean, shown here on the left, we probably had fewer and smaller continents. They did not form these land bridges like the Isthmus of Panama, or the Eastern Mediterranean, Israel, Lebanon, Syria, that blocked the circular currents of the tidal bulge, which dissipates the tidal bulges today. Remember, the tidal bulges in the North Sea and almost anywhere are currently locally controlled. Okay? They are not made by big global parameters. Back in the Archean, it may have been different, and the tidal bulge may have circled the globe almost unimpeded, in particular with a closer and faster orbiting moon. The tides may have been higher, they may have been more frequent, and they may have come on earlier and faster. Okay, the rise of the tides may have been much steeper. Thirdly, of course, we had no vegetation whatsoever, right? No baffling, no reeds, nothing like what we have out here. Okay, and that, of course, takes a lot of energy away. The energy from the oceans, these big crashing, surfing waves, they would have gone far, far inland. Tidal zones may not have been 1, 2, 3 kilometers wide as they are today, but maybe 10, 20, and 30, washing in and out, and raking the continental margins several times a day. And second to lastly, continental plains were probably lower and had less relief as well. Why is that? It had nothing to do with the oceans this time. It had to do with the flexural strength of the continents. Okay, continents were hotter. They were not able to support mountain ranges as high as the Himalayas. Even the even lower hills were probably less frequent and less widespread as they are today, and therefore tides could have run far further inward than what is possible today. And lastly, an argument that is probably particular to my experience is tidal flats may have been sealed by biomats in a widespread fashion for hundreds and thousands and tens of thousands of square kilometers. And my experience is based on having examined these cyanobacterial mats in shallow water environments in various places of the world. Have you ever been there? They are like rubber mats, a centimeter thick or two, and extremely coherent, very resistive. And so anything sliding over it would not have torn it up. It would have just slid like an ice hockey puck. Okay? So these biomats may have sealed tidal flats and reduced basal friction for the water, but also for sediment transport. So the reasoning stands that Archean tides should have been far, far higher than today's, more frequent, and they should have shown a higher rate of coming on and of abating. However, we don't see that. That is, in the oldest shallow water sediments from tidal flats that we have, around 3.2 billion years old, the few well-preserved Archean tidal systems only show patterns consistent with a mesoscale, that is a 2 to 4 meter tidal range. Why? We do not know. The theory dictates that we should see high tides, but we don't. Food for thought. 2 or 3 sentences about the spin rate. The spin through the Phanerozoic, and here you see only the last 600 million years, is fairly well constrained. And we see that in growth rings of trees and in 365 or so per year. That is, as the climate changes seasonally, we have all these count rings, and we have corals, and we have all kinds of paleontological constraints. So as we go back through time here, we can see that the numbers of days per year, shown here on the vertical, on the y-axis, increases gradually, and therefore the number of hours per day decreases. You see that from 24 currently, right, all the way going down to 21. However, this diagram only goes to 600 million years, right? There's an inset up here that shows the same thing going back to 2000, but these data here are the same that are shown here. And the reason they have this inset up here is only to display these 3 data up here, okay? So when I put this diagram into our regular Archean or time axis here, this is the original diagram, that one is that inset, and that here is that red line. I end up in the Archean with about anywhere between 550 and 650 days per year, and therefore a length of the day of maybe 18, 16 hours. I didn't calculate that. Okay, this is all theory. We have no observations whatsoever. However, there's a wonderful experiment you can do. I don't know who of you has ever been to the basement of NOAA in Boulder, Colorado. NOAA, National Oceanic and Atmospheric Administration, and so there's a visitor center, and you can go down into the basement to the bathrooms, I think, and there's even a Cray 1. Do you know what a Cray 1 is? Of what age? Not anymore, right? It used to be the goddess of computers, and probably it has a computational performance like an iPhone or something like that. And so it's parked right next to the bathrooms here wow, it's a Cray, but we are identifying ourselves as old timers, I believe. So next to that Cray, which I photographed as well, there's this thing here. It's a sphere, and it's filled with what looks like shampoo. Okay? And neatly, it's pivoting on a vertical axis, and you have an iron bar. So you take that and you start turning, all right? So the outer plastic, the plexiglass, the polyacrylic shell turns, but the interior liquid doesn't initially. But then there's friction and it starts turning. So here you are spinning the Earth, right? And we all know that as long as you spin, if you don't spin Earth at all, you wouldn't have any horizontal stratification. If you spin it a bit faster, you get the Hadley cells and the west wind drift and so on. And if you just go all out, it was a Saturday morning, no one else was there. So if you go all out, you get about 20 narrow bands, okay? So these are bands of cyclones, just as the ones you get in here in Bordeaux as they slam into the coast. And therefore, in the Archean, we should have had narrow strings of climatic belts, high pressure and low pressure cells, cyclones and anticyclones, just each of them maybe a few hundred kilometers wide. And so the pressure differences should have been very high. The wind strength should have been very high, right? Interesting. However, we don't see that at all, right? And the reason we don't see it is that at that time, we either didn't have continents, or at least we didn't have enough continents that would have given a suitable ground to preserve Aeolian sediments, right? I would love to find really coarse-grained Aeolian sediments. Yeah. Today, currently, the strongest winds are experienced in southwestern Greenland, and there you get coarse-grained Aeolian sediments, coarse-grained sand. Okay, I am not aware of any actively transported granules or pebbles worldwide. Altiplano in Argentina and Chile is also a good case, but from the Archean we should expect something similar, but we don't see that. Last major point, radiation and lighting. Lightning, okay? And I will not go into details in any of these three things, rather stay on the principles. And there's again a conundrum. There's again a contradiction and a mystery that we do not understand. Yet another one, so to speak. So if you want to consider the radiation doses that impacts on the Archean surface, you have to think about the sun and you have to think about the atmosphere, okay? And what I read from the literature, and there may be people here in the room who know lots more about that than I do, so this is just told from a layman's perspective. Solar radiation, as far as in a first order, was in the Archean not too much different, in particular in the UV spectrum, which we are interested in. The absorption was very different, right? Because our atmospheric composition was very different. And of course, the atmospheric chemists and physical chemists got to work and they did that modeling and they put into the model a so-called Archean reference atmosphere. Just look at the order of magnitudes of the different components, right? 10 to the 19th, 18th, 17th, 15th, and then the rest isn't really there, right? So from all I know, to the degree I can judge that, the composition of that Archean atmosphere is probably more or less correct, dominated by N2, and then quite a bit of CO2, lots of water vapor, and the rest doesn't really count. And here are the references to that. So we are particularly interested in what the Archean atmosphere does to the UV spectrum, okay? Currently, we are optimized for this year, visible light, but we are going a bit into a shorter wavelength radiation here, between 150, I think, and 350 in the next slide. And this is what they find out. This comes from Knossen et al., 2012. So here we have that wavelength spectrum between 180 and 320. So we're looking at UV light. And this here is the flux. And notice the flux spans a very wide range. It's logarithmic, and it goes over 12 orders of magnitude. Yeah. And so if we parked a satellite in outer Earth orbit and looked at the sun, it would measure that kind of spectrum. Yeah, it would be high. It would be really high in all wavelengths. If we have the present-day atmosphere, and we park the satellite here on ground and do a ground test. Its radiometer would record this spectrum here. It would record a lot of visible light, and then we go a bit into the soft ultraviolet, and then into the middle and the hard ultraviolet, and of course down here in the X-rays we are not getting anything, thank God, on the ground. Okay. Now, if we take the ozone out of present-day atmosphere, we are already getting a lot more of the soft UV. Okay, see that? And now let's move back into the Archean, where we didn't have any oxygen at all. Okay, so here are 3 lines, but don't be confused. The principal line is the orange in the middle, the Archean reference line, right? And then you can play around and reduce the CO2 to 1/10 of the orange value, or you can move the other direction and increase the CO2 to 5 times the orange value. And you see what it does. In general, you see whatever we have today, here we're not getting anything here on the ground between 200 and 280 microns on the ground. Back in the Archean, it was different. Anywhere, wherever you take your cutoff value, you were probably 2, 4, 6, 8 orders of magnitude higher. That's quite amazing, right? So in the soft UV, there was a minor difference, but in the middle and hard UV, it was a big difference compared to today. None of these values are really nailed into the ground, okay? And you can play around then with the biologically active wavelength spectrum. That is, you consider only those specific wavelengths that are really DNA harmful and so on. But it doesn't really make much difference when you just compare the value between what we are getting today and what we got back, what the surface received back in the Archean. You see that depending on the wavelength, this is over here to the right, you have visible light, but there wasn't much difference apparently. But back then, in the middle UV and in the shortwave UV, you had orders of magnitudes that were by many orders of magnitudes higher than as we receive today. Now, even the authors of that paper, they state carefully, it looks a bit dramatic only because we are currently not getting any hard UV here on the ground at all. Okay, that's why even if we get a little, it's 23 orders of magnitude higher. But make it 10 orders of magnitude higher. Make it 5 orders of magnitude higher. You go out into the Archean sunlight and you get your sunburn in a microsecond rather than in an hour. So what to do, right? And again, I'm not going to talk about the biosphere. I'll leave that difficult problem to any of my fellow speakers tomorrow or the day after. But the biosphere has found 3 strategies to deal with that problem: avoidance, armoring, and repair. Okay? Not going to say anything more. But it's interesting again. And lastly, here in terms of science, before we wrap this up, there's another curious thing. The Archean may have been full of lightning. There was a lot of volcanic dust in the atmosphere, a lot of turbulence, a lot of static electricity. So again, I described the climatic systems. There may have been, capital M-A-Y, a lot of lightning strikes. Now, lightning strikes have some interesting effects, or rather the strong electromagnetic fields associated with them have some interesting effects on the biosphere. If you take a typical lightning strike and you impact it on a shoreline, on a sand, on a water-saturated sand, a typical lightning strike with 30 kV or so, it typically kills everything within the red zone, which may be anywhere, depending on the salinity and the degree of water saturation, between 2 and 10 meters in radius. It doesn't hurt anything outside between 20 and beyond 20 meter radius. Then there is this hemisphere here, that bowl, within typically between 3 and 5 meters or so radius or distance from the impactor, from that lightning strike. You see it here, I said 0.3 to 0.8, in which the electromagnetic field strength is just enough to injure life, that is single cellular life. That is, the cell walls get nicked. Okay, the cells don't explode through the big change in electromagnetic field variability as in the red zone, and they are not left unhurt either, they just get nicked. And that in turn is interesting because it enables you to exchange chromosomes, or DNA information, and then to repair yourself. So indeed, some of the most primitive organisms show a very high resistance to electromagnetic fields, which has been unexplained. This process, by the way, that is exposing organisms to strong electromagnetic fields is a widely applied industrial process. It's known as electrophoresis. Okay? So, that would be a nice way to get mitochondria and chloroplasts into the eukaryotes or into the algae. This is an interesting phylogenetic tree. You see that interesting root down here. That is something else to discuss. But you see these strange linkages between different trees, between different branches of that tree. And electrophoresis, or whatever happens when you have a thunderstorm going on these Archean beaches, may be a good way to explain that. Remember, even if that bowl was very narrow, it's about 700 liters. I calculated that back of the envelope. And each cubic centimeter of water contains how many cells? The biologists should know. Yeah. It's not just 2 or 20, it's in the millions. So, summary, rock record. Too little, too late. Yeah, maybe remember that. We geologists cannot really say much about astrobiology or the origin of life because our rock record sets in too late. In other words, even the oldest rocks that are suitable to reading and evaluating traces of life already have life in it. It's not that we can go back to the very oldest rocks and say, all right, this here is the sterile Earth, and then go stratigraphically upward and see where life was invented. Even the oldest rocks already have life. And then, so it's too late, right? And it's too little too. I'll show you, we just have 3 or 4 regions on Earth that we can derive information from. And then, of course, we can do something about it. So look at the rock record. I wrote Ishua, Pilbara, Barberton, and Transvaal. Where do they place on the time axis? Our oldest surface rocks are from Ishua. It's a rather inaccessible place right next to the glaciers of the West Greenland ice shield. I have never been there. It's humongously expensive to get there, accessible for only about 6 weeks per year. Otherwise, it's just icy. So, but Ishua is between 3.85 and 3.75 billion years old. Then we have the Pilbara in Australia, anywhere between 3.6 and 3.1. And pretty much at the same age, we have Barberton in South Africa, anywhere between 3.57 and 3.2, more or less. And then these are the 3 big data points that we have for the early Archean. And these are fragmentary, these are all greenstone belts, but it's all we have. And of course, we don't have here a continuous rock record for every second of 300 million years in Barberton, right? There are big gaps in here between where time periods of 20 and 50 and maybe even 100 million years were left unrepresented. And only then gradually the situation improves by getting the first stable flat-lying sediments in the Transvaal supergroup in South Africa. South Africa, the Kaapvaal Craton there, forms our oldest stable continent. And when you land in Johannesburg, you are landing on rocks that are about 2.5 billion years old, and they are still flat-lying. Okay, they have not been deformed. This has been a really stable microcontinent. So what kind of rocks do we find in there? We start our rock record essentially with volcanic rocks, and that is not surprising, right? I showed deep water clastic sedimentation, so these are turbidites and debris flows, all of them of volcanic and volcanoclastic composition running down into the funnels between the volcanic edifices. We have shallow marine but volcanic platforms. Think of Ontong Java, of Kerguelen, of Iceland, maybe of any shallow water volcanic platform. And we have volcanic calderas, and these volcanic calderas already contain traces of life. Then we go gradually into carbonates, right? And we see in particular, as we develop these stable shallow water platforms, they immediately get covered by thick carbonate sequences. Carbonate is life, and carbonate means drawdown of CO2, temperature. Biosphere takes control of the temperature of the planet. And then siliciclastics, tide-dominated shores show up here around 3.2, yeah, indicating that we did have something of a continent or a microcontinent or something. And the truly continental habitats or environments like evaporites and aeolian-dominated, they barely show up here, possibly, yeah, in Barberton at 3.1 or 3.2 rather, and then we do have some records here in the Transvaal supergroup. So what to do about this? You know, I'm a Barberton specialist. I focus on these rocks, and we need fresher rocks. We need to get out of that oxidative weathering zone. Oxygen is really bad. I say, and take a deep breath, for our rocks. And we need to get through that weathering zone, and we need to have continuous sequences. Think of the tides, you know, think of rhythmicity and lamination. So what we did in the last 2 years or so was putting together a drilling proposal. Remember, we don't have to drill deep. All the rocks are vertical. We have to drill sideways into them. And we got together as an international group. There's a consortium called ICDP, International Continental Drilling Program. It has about 28 member states, and they all pitch in money, and there's a review process and so on. So I first had a workshop, and then I submitted together with my co-authors a drilling proposal. This year is the status. We had our workshop in October. We turned in the proposal January 15th, and we are all sitting and biting our nails to get the funding decision, which would account for about 50% of our drilling expenses by late June. So up to the right, you see some of the 50 people or so that participated. The French, by the way, are quite well represented. You see Stéphane Lalonde from Brest, whom I will see the day after tomorrow. There's Camille. Camille, do you see yourself here? Okay. There's Emmanuel from Liège, and there's Johanna Marin-Carbon from Saint-Étienne. Okay? And they're postdocs, of course. So we gave ourselves a structure. We have our subgroups, live, paleo environment, sediments, and hard rock, and we just see what will happen. So what we're going to do is then drill sideways, obliquely into these vertically standing rocks with a small drill rig. I hope it will look cleaner than this picture here. That was from a previous drilling project finished in 2012. So 3 slides to wrap up. Big problem in one slide, conclusions in one slide, and a summary slide. Here's the big problem. By now you know that we have this really poor rock record for the first billion years of our Earth history. We therefore cannot really say anything about rates. Okay? So rates, anything related to the change between 2 data points, rates, variability, anything related to the vague concept of evolution, we can't tell because we only have 1 or 2 or 3 data points. So we don't, even though we have some thoughts, maybe even data on climate, we know nothing about climatic variability in the absence of a potent biosphere. Remember, we don't have any biosphere, possibly, because the biosphere didn't occupy the continents, probably. But we don't have much of a continental record. For all I know, the Archean continents, as small and few as they were, could have been covered in green things. But we don't know. Okay? So climatic variability in the absence of a stabilizing biosphere would be a big research topic. Growth rates of continents, yeah, and all the subordinate parameters attached to the presence of continents, that is mostly weathering, for example, yeah, and climate control and biospheric control, is a big orange question mark. And then, of course, the colonization, right, of continents. So in conclusions, you all have seen, if you ever looked at the web page of this block course here. You have all seen this image as one of 5 or 6 or 7 images. Sorry, it's all wrong. Okay, I got your attention. What's wrong about it? Now it's your turn. There are mountains. What are you saying? No mountains. What should be there instead?
The color of the sky.
Well, then let's stick with the mountains. Wait. So, okay, no mountains. What would you like to replace the mountains by? We're the geologists. These are what kind of volcanoes? Camille, you're a geologist. These are stratovolcanoes, look like Vesuvius or Etna, right? No stratovolcanoes. You had shield volcanoes like Hawaii, or you had volcanic plateaus like Ontong Java or so on. So can't be, right? Unlikely. Yeah, there were some, but surely there were some over that 600 million year time period, but I wouldn't put them in an emblematic picture, okay? Who said about the blue sky? And why do you think that?
Because I think blue is from the azote or the nitrogen. So
Maybe. So
it water, right? If it was full of dust and soot, it would be
dust and soot and water vapor. I think the Archean was really dark, right? Dark and muggy.
Blue is diffusion by gas. So if any gas would result in a blue color sky, if you don't have aerosols. Or
Yeah, but we think we had lots of aerosols. We talked about haze, remember, and so on. So yeah, sure, there were some bright moments in the Archean, but again, as a symbol, I would replace this by some different weather pattern. What else?
the stromatolite would have been fried by the UV.
And still, we have stromatolites, right? What else is wrong?
Not necessarily above water.
Yeah, okay. Well, shallow water, they get ripped up and so on. But, and yeah, you know about the mechanisms. Avoidance, repair, and something else. What else? Think about that moon and that nice water surface. There should have been some waves, right? It's unlikely that the Archean was characterized by a windless water surface. And lastly here, these stromatolites. Stromatolites are fine by 2.8, 2.9 billion years, but for the first 1,000 million years of Earth history, I wouldn't put them that prominently into that picture. Okay? So, sorry, it's again the same thing as with the tidal faucets. I have no better picture to replace this by. Not yet. Okay? Summary, we started out with the cool young Earth. We then talked about the interaction of magma and water. We then talked briefly about meteorite impacts and the spherules. I then went into tectonics, and I showed you the partial convective overturn and the dropping and the lava lamp tectonics. We then talked about volcanism and the interaction with the atmosphere. And the atmosphere, of course, has interaction with the geosphere and the weathering, feldspar weathering, CO2. Then we talked about tides and the moon. We talked about the radiation and how it may have been very different. And we ended up here discussing the true Archean environments. So this is all I have to say. Thank you very much for your attention. If you want to contact me, I work and live, almost live in this beautiful department here, Jena University, and my name is Christoph Heubeuck. Thank you.